We start the discussion with background and motivation of principal component analysis with the mobile survey example. We discuss the data with one dimension, that is price, and two dimensions, that are RAM and price, and extend the case for a three-dimensional data where we have RAM, price, and brand as three dimensions. Next, we discuss the principal component extraction process, eigenvalues, and a two-dimensional data, and extend the same analysis to a three-dimensional data. We conclude the discussion with K-means clustering algorithm. In this video, we'll introduce the principal component analysis. We'll provide the background and motivation for the same. Let's suppose you are a player in mobile phone industry and it matters to you what kind of prices, RAM, brand, features offered by different brands. You are looking for some kind of segmentation and positioning of your product. You have also some buyer survey data where you are examining the scores. Let us see what kind of questions you would like to answer. First, you'd like to know for the individuals, for the target segment customers, which parameters hold most importance, for example, price, etc. You'd like to cluster your individuals along different dimensions. You'd like to segment the customers, different particular segment of homogeneous set of customers, where you can target your product, that is mobile phone. You'd also like to know which particular attributes in your data, such as price, brand, features, and so on, that is important to that particular target segment. Also, you'd like to know, can you segment that into a competitive scape where you can position and find your right set of competitors where you would like to operate. You'd also like to know, are there any hidden dimensions in the data, for example, value for money, which is not just a single dimension, but a combination of multiple things, but gives you the taste and preference of your target set of consumers. To begin with, typically your data would have two dimensions. One is the individuals, the survey data from users, where you have some information about your users, probably their demographics, their purchase preferences, and so on. And the data about mobiles, brands that are targeting in or operating in the segment that you want to operate, or you are exploring the market. Typically, when you are constructing PCAs, either of these dimensions, for example, if there are 30 individuals, this dimension can fully describe your data. Or if you have, let's say, 10 mobile phone brands or 10 mobile phone products, that dimension can also fully describe data. Now, the way PCA happens, it would look at the variable or dimension that has smaller number of sort of dimensions. In this particular case, it would be variables, most likely because you would be conducting a survey of lot many individuals. So the product would be lesser number, or rather what we call as variables would be lesser. So let's say you have 10 mobile brands or 10 mobile phones, the maximum PCAs would be 10. So the dimension along with which there are lower number of data, sort of lower number of columns, or you can say their dimensions is lower, that would determine the maximum PC dimensions. So in this case, if you have 100 individuals and 10 variables, that is 10 mobiles, the dimension of mobiles is less, so it will determine that maximum PCs would be 10. To begin the analysis, let's start or think of a 1D plot. Let's suppose for all of these individuals, price is the maximum most important determining dimension that defines all the individuals in this market. Obviously, this is a spurious case, not true, but it simplifies the analysis. If everybody is driven just by price, you can plot mobile phones product that you have simply on this price axis and create clusters of variables. That means which brands should be put together and in which segment you would like to operate. You can create these different segments along the price line. You can also classify individuals on this price line, which individuals are price conscious and which are on the higher side of the price. So then analysis is quite simple. You have only one dimension that you need, price, and it determines all the analysis that you want to do in this market. Let's suppose you add one more dimension. You find that a lot of people like how much RAM is being offered. And now you can plot or sort of put your data points along the 2D plot where the x-axis is price, y-axis is RAM, and different mobile phone products can be put here. Even here, it is not that difficult. If they are put like this, you can cluster them. And similarly, once you can also find individuals who have different preferences for RAM and price. You can put individual 1, individual 2 on these axes and cluster them as well. So you can have, let's say, for example, one kind of individual located here. Then you may have another set of individuals located here. The point I'm trying, not only you can cluster segment the mobile phones, you can segment cluster individuals also, and your analysis is done. But the complexity of analysis increases. And as you keep on adding more and more dimensions, let's say another dimension is brand, such clustering would not be easy, it would be difficult. And imagine having 10 such dimensions where you have to cluster individuals and products, variables. Now, then in that case, the right approach would be to find those hidden dimensions. So for example, if there are 10 variables, you'd like to find probably one, two, not more than three dimensions or variables that are not exactly known to you, that are latent, so they are not observed, but they can explain these 10 dimensions. Maybe not 100%, but maybe 80% of variation in this data with 10 dimensions can be explained by those limited number of 2 3 dimensions. More specifically, if you have a only 2 dimensions, then you can very well plot on 2D plot easily, like we are doing right now. So this is called dimension reduction, and for this dimension reduction we require the help of PCA analysis. So in this video, we understood the background and motivation of PCA analysis, why would need, what kind of situations we would require PCA. In the next set of videos, we'll try to find out how to construct PCA from a given set of data. In this video, we'll talk about extraction of PCA in number of steps. First step here is finding the center of the data. Recall that on the axis of RAM and price here is x-axis and RAM is y-axis. We have our points here, mobiles like Xiaomi, Infinix. These are just randomly put here. So these are the points. There's no particular significance to it. Now we have 3 points here. 3 points here. We can draw their projections on x and y axis. Let's suppose on x-axis we have projections like x1, x2, and so on up till x6. They can be more or less. Similarly, on y-axis, we have projections like y1, y2, y3, and so on. The first thing to find the center is to take the average of these x-axis coordinates, that is x bar equal to x1 plus x2 and so on up till xn divided by n. Similarly, take the average of these y coordinates to get y bar equal to y1 plus y2 and so on up till yn divided by n. So we'll get this coordinate of centroid, which is x bar comma y bar. Now that we have obtained the centroid, the next step here is to shift the center to the origin. We'll shift the center to the origin in a manner that relative position of these points does not change. So the center is the entire system of this entire system is shifted to the origin, but the relative position of all the other points remain intact. So we shift it to the origin. Once the data is centered, we need to find the PCA by fitting a line. The question is, what should be the right criteria that decides which is the best fit line? Let us go back to the first argument where we said that if there is only one axis, let's say that is the price axis, which describes all the variation in data, all the points will appear like this. This suggests that one way to argue whether a PCA dimension captures or extracts all the variation in the data is how close it is to these points, which means the distance between the point and vertical distance between the point and the axis. One extreme case in that case would be that the distance is 0. That means the entire data falls on one particular line, which becomes your PCA. And in that case, entire 100% variation is explained. However, such extreme cases would not be possible. And while you're fitting the line, some point would be slightly above or below. But more importantly, we need to minimize this some function of this distance. So suppose, let's start with this example. Suppose this is the point and the distance of this point from center is B2. Origin is our center, so this distance is B2. Now, let's say we randomly choose this line as our PCA. This is a randomly chosen line, as of now, not the best fit line yet. If I drop a vertical perpendicular projectile here, this projectile has a length of A2. In general, if the point is 1, it can be A1, A3, and so on. It can be any generic AI. The objective here is to minimize this AI or A2, A3 in this case. But if you recall, when we are fitting this line, we are rotating this line to obtain the best fit line, which will minimize this distance. However, the location of this point vis-a-vis this axis remain intact, which means this distance P2 is not changing. This is constant. And if you recall, there was something called Pythagoras theorem, which suggested that a square plus d square equal to b square. So we are choosing generically, for example, in this case, it will be a2 square plus d2 square equal to b2 square. Or in this case, it will be a1 square plus d1 square equal to b1 square. So if you sort of collect these thoughts, you can see here that minimizing a is same as maximizing d because b remains constant. What is d? D is the distance of origin from this projectile point. For example, in this case, this distance would be this much. Mathematically, maximizing this D is easier than minimizing this A. B remains constant and therefore minimizing A is same as the maximizing D. And we'll follow this objective now. So once we have chosen this, the right approach would be to minimize the sum of square of all these distances. So if there are I such points, then d1 square plus d2 square and so on up till di square. Why not summation of d1, d2? Because then negative distances on this side and positive distances on this side may cancel each other out, which will not give us the right picture. So maximizing the summation of square, or what we call as sum of square distances, is the better objective. Now we keep on rotating this line in any direction till we find the point which, or the slope, rather the slope alpha, which maximizes this. Once we find this line, we'll be able to ascertain the slope. Let's suppose this, we find the line that maximizes this distance, what we call a sum square distances, is 1 by 3. This also means that if the slope is 1 by 3, we move in this direction. For every 3 step we move here, 1 step we move upwards. So every 3 step when we move in this direction, for every 3 step horizontal distance, 1 step vertical distance is covered. This is to suggest that this line, that what we are calling as first principal component, is a linear combination of these two x and y axis. X axis is here for our argument is price and y axis is RAM. So this line sort of, you can say, is a linear combination of these two axes. Now suppose there were more such axes, then this would be linear combination of multiple such axes, maybe 3-dimensional, 4-dimensional, but this would be slightly difficult to visualize here. What about this length b? B remains constant, and in this case b equal to a square plus d square, which is 1 square plus 3 square, because slope was alpha was 1 by 3, which is 10, and therefore b remains square root of 10, which is 3.162. Now for maximization of this kind, we need to fix some limit on b, because if we do not fix any limit on b, this maximization can take infinitely large number of length. So to put some, so we need some kind of constraint, and we put that constraint that b should be equal to 1. Once you put this constraint, then a will also be changed. So it will be 1 upon square root 10, which is 0.316, and d will be equal to 3 upon square root 10, which is 0.949. These will be the loadings of RAM and price on principal component. So whatever your variables are, these will be the loadings of that on PC1. Also recall, earlier we computed sum of square distances, d1 square plus d2 square and so on up till di square. If I divide it by n minus 1, this becomes the eigenvalue of PC1. This eigenvalue has a very important role to play in the understanding of principal component. Let's suppose in my data there are 10 such dimensions. In this case, there are 2 dimensions only, but let's suppose there were 10 such dimensions or n such dimensions. Summation of eigenvalues all for all those PC1s, PCIs, PC2, and so on up till PCN. If I sum up all of them, that means total sum of eigenvalues of all the maximum possible vectors. In this case, it will be 2. If there are 3 dimensions, then it will be 3. If I divide any particular principal component by the total sum of eigenvalues, if I divide the eigenvalue of a particular vector, it gives me the variation explained by that particular principal component. For example, here, let's take a simple example here. Suppose PC1 has an eigenvalue summation of 20, PC2 has an eigenvalue summation of 5. Then the total, if there are only two PCs, the summation of PC1 eigenvalue plus PC2 eigenvalue is 25. And then we can say that PC1 upon this 25, that is 20 upon 25, which is 80%, variation is explained by PC1. And the remaining 20% is explained by PC2 if there are two such principal components. So this is the significance of eigenvalue. It plays a very important role in understanding the variation explained by a particular principal component. To summarize, in this video, we concluded with our first step of extracting the first principal component. In the next video, we'll see how to extract more principal components, and we'll also understand more about the eigenvalue and extraction of second principal component and so on. In this video, we'll conclude our discussion of PCA extraction. Recall, in the previous video, we concluded our discussion with the help of eigenvalues. We said that we'll minimize these sum of square distances di, and we said that if there are, let's say, only two principal components, why? There are only 2 dimensions RAM and price. Suppose there were more such dimensions, 3, 4, then accordingly the same number of principal components were there. Suppose 3 dimensions with brand also included, there will be 3 PCs. Now here we have only 2 dimensions, so we'll have 2 PCs. First PC has sum of square eigenvalues as 20. Eigenvalues, recall, they were sum of square distances divided by n minus 1. So PC1 has this eigenvalue of 20, PC2 has 5. So total PC1 plus PC2 is 25. So that means 80% of the variation, overall variation is captured by PC1 and PC2 covers 5%, 20%, which is 5 upon 25. With this, now let's start talking about PC2, how to estimate PC2. PC2 is a vector which goes through the center and orthogonal to this PC1. So with simple slope logic, slope of PC1 into PC2 has to be -1. For example, if PC1 is y equal to x, then PC2 would be y equal to -x, and so on. So PC1 had a slope of 1 by 3, so we can safely say that PC2 has a slope of 1 minus 3 and it goes through origin. And with that logic, the loadings can be calculated as on x-axis the loading as 0.316 and on y-axis as minus 0.949. The next step is to rotate these PCs so that the first principal component PCA1, which explains the maximum variation, becomes horizontal, and PCA2 then automatically becomes vertical. Now recall what we had was projections of our points on PCA1 and PCA2. These were the points from which we maximized the sum of square distances. So we have these projections on revised PCA1, PCA2 axis. So now this PCA1 is our new x-axis and PCA2 is our y-axis, and we have the projection points here. Using the projection point, suppose this is the projection point for point 1 and this x-axis PCA1 and this is for point 1 on 2, we can identify the coordinates sample 1. Similarly, let's suppose this is the projection on y-axis for point 2 and this is the x-axis projection of point 2. We can identify point 2. In this manner, we can regenerate all the original points on these revised axes which constitute PCA1 and PCA2. A better way to identify how many principal components added. So let's say you want to add a third factor and so on. That third factor should be orthogonal to these two and should go through origin. Now, how many factors are needed? So maximum, let's say you can calculate n factors in a given the dimensions of data. How many factors do we need? For that, you can see the numbers, how much variation is explained. You would not like to have factors which explain 1% or 0.5% of data, not so useful. So you can just examine the numbers, and also there's something called scree plot, which is the bar plot of these PCAs. It appears like this. So you have the variation explained here, or the eigenvalues or the variation explained on the y-axis, and for each principal component. Now you look at this movement, you look at this curve, and where this curve is the most steep, you keep. So for example, if the curve is most steep, you keep on adding, and where it's too low, it becomes flatter, you stop there. So once it reaches a very small point and you stop here, somewhere down the line here, stop. So this knee kind of structure, there's a knee kind of structure, elbow kind of structure is there, so you stop at that point. In general, you can set up some criteria. For example, you may decide that I would go up till factor with the explanatory power 10% or 15%, not below that. Somebody may go up till 5%. It is depending upon the context. You can keep on adding the factors, but recall, adding each factor has a cost. It introduces noise and more difficulty of data collection and interpretation. So you'd like to have your number of factors in a very parsimonious manner. So it should explain the data to a certain minimum extent. Finally, to conclude the discussion on PCA extraction, first an important point, the PCA plot will convert original variables, like in our case price and RAM, into new dimensions that are perpendicular and uncorrelated. So each PCS can explain maximum of data. PCA1 obviously is more important than PCA2. So the distances between across PCA1 are given more weight. Suppose there are 3 points in fact, A, B, and C, and between them the distance is A here and A here. But because this PC1 has more important as compared to this PC2, this A distance will have more meaningful or more weight between A and B here on this axis as compared to the A distance here. Lastly, maximum number of PCs that you will obtain will depend on whichever dimension is low. So suppose there is an individual and variables. So suppose there are 30 variables and 10 variables, you would have maximum PCs as 10. Suppose there are 5 individuals and 20 variables, then maximum PCs will be 5. In general, as a practitioner's rule, most likely individuals whom you are surveying or collecting data will be more, while variables would be less. So in general, as a thumb rule heuristic, depending upon the number of variables, the maximum number of variables, that will be your number of PCAs. So with this, we conclude our discussion on PCA extraction. Next, we'll move on to clustering discussion in the next video. In this video, we'll briefly introduce the concept of k-means clustering to the extent needed for understanding the implementation. The following steps would be required to construct k-means clusters. First, we'll randomly choose k-centroids. That is a choice of researcher. one centroid will be, for each cluster there will be one centroid. We'll create k such clusters by assigning the observations that are nearest to a chosen cluster. Then we'll compute the new centroid for this cluster and again assign the observations to the nearest centroid. And we'll keep repeating it until the new centroids don't change and observations don't change or switch their groups or clusters. Let's see how it works graphically. Look at this particular XY space in 2D plane. It's easier to visualize in 2D plane. There are these observations scattered here. As a first step, let us start by choosing a random centroid. So suppose I choose, it appears that this is a particular cluster, so one centroid here, and these are purely randomly chosen, one centroid here. The color coding scheme clarifies that when we are choosing clusters, how we are choosing it, and this one centroid. Now it is quite obvious that if this is centroid, these four observations will be part of it. If this is centroid, probably these observations, these color coded observations will be part of the group. If this is the centroid, then probably these two. If this is the centroid, then probably these two. So we have these four clusters depending upon the choice of initial k value of 4. We have four clusters. In the next step, once we have those clusters, we'll calculate their centroid. So for example, for this group, this may be the new center. For this pinkish kind of observation, this may be the new centroid. For these red colors, this may be the centroid. For the blue observations, this may be centroid. So now we have new centroids, and the next step in the second iteration, what you need to do is for each centroid we need to recalculate the distances of from each of these centroids for each of the observations, and again we'll assign those observations that are nearest to each group, and therefore new cluster will be created. Them each cluster will be probably assigned new members now. For example, here not many changes. Here a little bit of observations change. Here also there's minor changes. So again, four clusters are there with some new observations, and we keep on doing that. With new centers, we'll again calculate the centroid, and then once we have calculated the centroid, we again calculate the distance of each point from the centroid, again regroup the members. So again, new groups are appearing, new clusters are appearing. Then again, you get the centroid. As you keep on repeating that, there would be a point when say, the clusters would stop changing. That means the centroid would not move, and the members that are there in the current cluster, they would not change. There will be no switching of members across clusters, and clusters will stabilize. Once this happens, you have arrived at the clustering method. Such clustering method is also referred to as k-means cluster. The number of k clusters the choice of that is determined initially when you start with. The clustering method is heavily dependent on the choice of number of clusters and also the initial position of centroids that you choose. If the initial k and number of k is not chosen effectively, that may lead to poor clustering, more number of iterations, and choosing such initial k clusters and their location depends on a priori knowledge about the data. Lastly, as we have kept repeating, to find these clusters and clustering the observations, we need a distance measure. We have been using vaguely the term distance. In two-dimensional plane, a very often employed Euclidean distance measure is xa minus xb raised to the power 2 plus ya minus yb raised to the power 2, square root of that. So in 2D coordinates in the plane, it is simply like this. AB distance is computed at, like, using Pythagoras theorem, a square plus b square, this is equal to c square, and this a square is x1 y minus x2 plus raised to the power 2 plus y1 minus y2 raised to the power 2, xa minus xb raised to the power 2 plus ya minus yb raised to the power 2. So this would be the distance between a and b, which comes simply from Pythagorean distance. Similarly, if you have j-axis, you can use this generic formula, summation vpj minus vqj raised to the power 2, summation of all those squares and then square root. For example, if you have three sort of features or three axes, then you can use xa minus xb raised to the power 2, ya minus yb raised to the power 2 plus za minus zb raised to the power 2, so and square root of that. So with this, we conclude the k-means clustering discussion. We understood how to form clusters. We also understood what kind of distance measure we are using, and how by changing the centers and assigning new members to cluster, and then again finding the centroid of that cluster, and then again choosing the members. In this fashion, we optimized, and through iterative process, we achieved this k-means algorithm and find the cluster. The distance measure used here was Euclidean distance. We understood how to compute Euclidean distance also. Let us summarize what we discussed in this lesson. You are a mobile phone manufacturer and you survey various target populations for different mobile offerings from competitor segments. You'd like to position your offering suitably in the target segment. You'd also like to analyze the target customer segment with your data facilitated by PCA and clustering analysis. Lastly, you want to examine latent dimensions of your data. We also noted that just with one dimension, that is price maybe, and two dimension with is RAM and price data, this kind of analysis is easier. However, as dimensions increase, complexity of this exercise increases. Thus, we needed principal component analysis. The following steps are needed in the PC extraction process. First, we find the center of the data and shift it to the origin in a manner that relative positions of all the points on XY axis remain unchanged. In the shifted data, we find the principal component as the best fit line that maximizes the sum of square distances, that is SSD, from the origin. Next, we find the second PCA as the line that goes through origin is orthogonal to PC1 and maximizes the sum of square distances in a similar manner as done earlier. Now we project the data points on PC and PC2. Next, we rotate the PC1, PC2 in a manner that PC1 is horizontal and PC2 is vertical. We find the revised data points back using the projections of PC1 and PC2, thus obtaining two coordinates X and Y on the new axis, where X-axis is PC1 and Y-axis is PC2. One can also find PC3 if required in a similar manner, that is, a vector orthogonal to PC1 and PC2 passes through origin and maximizes the sum of square distances. Here, sum of square distances divided by n minus 1 is the eigenvalue, and it helps us in examining the total variation in the data explained by the individual principal components. Finally, we conduct the k-means clustering exercise. For the same, we randomly assign the predetermined number of centroids to the data plotted on xy plane. Next, we computed the distance of each point to these centroids, and each point is assigned to the nearest centers. We can compute the revised centers of the data. We keep repeating this exercise till the centroids are steady and no switching of observations across clusters occur. This will lead us to the final set of clusters.